Hi students, so myself is Vedamurthy. You are watching the video Chemistry Class 11 Part 1 Unit 2 The Structure of Atom. In that we are going to study shapes of atomic orbitals. Welcome students. So today the main topic uh, which is coming across in structure of atom, that is shapes of atomic orbitals. The orbital wave functions are psi for an electron in an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave functions as a function of r. R is the distance from the nucleus. As a function of r are different. So you can refer the figure, first one, the plots of the orbital wave function psi r, and the second is the or variation of the probability density of psi square or as a function of the distance r of the electron from the nucleus for 1s and 2s orbitals. You can observe those plots how are it is made. According to German physicist Max Born, the square of the wave function, that is psi square at a point, gives the probability density of the electron at that point. The variations of the psi square as a function of r for 1s and 2s orbital is given in the second diagram or figure. Okay, so please look into that. So psi square r versus r nanometer. Here again you may note that the curves for 1s and 2s orbitals are different. 1s and 2s are different is there. Next, also it may be noted that for 1s orbital the probability density is maximum at the nucleus and decreases sharply as we move away from it. On the other hand, for 2s orbital the probability density first decreases sharply to 0, again starts increasing. So after reaching a small maxima, it decreases again and approaches 0 as the values of the r increases further. The region where this probability density function reduces to 0 is called nodal surface or simply nodes. In general, it has been found that ns orbital has n minus 1 nodes. Okay, so that is the number of nodes increases with increase of the principal quantum number n. In other words, the number of nodes of 2s orbital is 1 and 2 for 3s and so on, 3 for 3s and so on, 4s. These probability density variation can be visualized in terms of charge cloud diagrams. We can refer the figure second one. So this you can refer these two diagrams. This probability density variation can be visualized by 1s and 2s by the example A. So figure A, 1s and 2s, how the uh, density of the dots in a given region represents the electronic probability density in that region. Okay, so this is the probability density plots of 1s and 2s atomic orbitals as mentioned in the figure A. So here the density of the dots represents the probability density of finding the electron in that region. Okay, so second, so here boundary surface diagram of constant probability density for orbitals give a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or counter surface is drawn in space for an orbital on which the value of probability density psi square is constant. So in principle, many such boundary surface may be possible. However, for a given orbital, only that boundary surface diagram of the constant probability density is taken to be good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say 100%. 100% is fully occupied. You can see the figure 2 boundary surface diagram 1s and 2s orbital. This is one. Okay, students. Yes. So if someone can ask the question, why do we not draw boundary surface diagram which bounds a region in which the probability of finding the electron is 100%? So we can answer this question like this: the probability density psi square has always some value, howsoever small it may be. So at any finite distance from the nucleus, it is therefore not possible to draw a boundary surface diagram of rigid size in which the probability of the finding electron is 100%. Students, now the boundary surface diagram for a s orbital is actually a sphere centered on the nucleus. In two dimensions, this sphere looks like a circle. It encloses a region in which the probability finding the electron is about 90%. Thus, we can say that 1s and 2s orbital are spherical in shape. So, spherical in shape. This 1s and 2s orbitals are spherical in shape. Both the diagrams are same only. Okay, students. Yeah. Now, so in reality, all the s orbitals spherically symmetrical, that is, the probability of finding the electron at a given distance is equal in all the directions. So, also observe that the size of the s orbital increases with increase n. That is quantum number. That's why 4s is always less than 3s. 3s is less than 2s, and 2s is less than 1s. And the electron is located further away from the nucleus as the principal quantum number increases. So boundary surface diagram for the three 2p orbitals, that is 2px, 2py, 2pz. So L is equal to 1. When 2p orbitals comes, L is equal to 1. So I can see the refer the these three pictures. Sorry, pictures. Yes, you can refer these 2px, 2py, and 2pz. The boundary surface diagram of the three 2p orbitals. So here in these diagrams, the nucleus is at the origin. So here, unlike s orbital, the boundary surface diagram are not spherical. Here you are seeing the picture of this one. Here you are not finding any spherical shape. So here there are lobes are there that will come. So here, unlike s orbital, the boundary surface diagrams are not spherical. So inside each p orbital consists of two sections. Two sections. So those two sections either side, those are called lobes. This is lobe. This is one of another lobe. This is one lobe. This is one lobe. So either side of the axis. Okay. So the probability density function is 0 on the plane where the two lobes touch each other. The size, shape and dense energy of the orbitals are identical. They differ, however, in the way that the lobes are oriented, since the lobes may be considered to lie along the xy and z axis. So they are given the designations like this: 2px. So 2px, 2px. This is 2px. So the two lobes are on either side of the x and y axis along the z axis. Same way 2py. 2py is a cross which is come across the y axis and towards z and x axis. That is another shape. So 2pz, 2pz above and below the, in the z axis both are coming, lobes are coming across in towards z axis is centered with the x axis. That is third one, 2pz. So it should be understood that, however, there is no simple relation between the values of the, so here ml is equal, ml is -1, 0 and +1, and the x, y and z directions. For our purpose, it is to understand to sufficient to remember that, because there are three possible values of ml, that is -1, 0 and +1. So therefore, three p orbitals whose axes are mutually perpendicular, like s orbitals. P orbitals increase in size and energy with increase in the principal quantum number. Hence, the order of the energy and size of the various probability is 4p is more than 3p and 3p is more than 2p. Further, like s orbitals, the probability density functions for p orbital also pass through the value 0, besides at the 0 and infinite direction, as the distance from the nucleus increases. Here, the number of nodes are given by the n-2, that is, number of radial node is 1 for 3p orbital, 2 for 4p orbital, and 3 for 5p orbital, and so on, etc. For L is equal to 2, the orbital is known as d orbital. When L is equal to 2, the orbital is known as d orbital, and the minimum value of the principal quantum number n has to be 3, as the values of L cannot be greater than n-1. Here in d orbitals there are 5 ml values, that is -2, -1, 0, +1 and +2. For L is equal to 2, and thus there are 5d orbitals. The boundary surface diagram of the d orbitals are given in this picture. So you can see this is dxy, can named as dxz, dyz, dx square minus y square, and the next one is dz square. Last one is dz square. This is dz square. So the 5d orbitals are designated as dxy, dyz, dzx, dx square minus y square, and dz square. The shapes of the first 5, the first, here you can observe the shapes. The first 4 are very similar, to each other, whereas the fifth one, the last one, this is one, what is that, dz square. Dz square is different in shape, but all the 3d orbitals having, for where the n is greater than 3, 4d and 5d etc., also have shapes which is similar to 3d orbitals, but the different in the energy and size. If it is 3d, its energy is different and its size is different. 4d is different, 5d is different, each are different. Besides the radial nodes, that is probability density function is 0. The probability density function for the np and nd orbitals are 0 at the plane s passing through the nucleus or origin. For example, in case of pz orbital, xy plane is a nodal plane. In case of dxy orbital, there are two nodal planes passing through the origin and bisecting the xy plane containing z-axis. These are called angular nodes, and number of angular nodes are, for p orbitals, 2 angular, and angular nodes for d orbitals are 2. So angular nodes for p orbitals is 2 and d orbital also is 2. The total number of the nodes are given by n-1. So that is sum of L of the angular nodes and n minus L minus 1 radial nodes. This is about the shapes of the atomic orbitals. So we learnt in this 1s orbital, 2s orbital, okay, 2p orbitals, 3p orbital, 4p orbitals, and same way. So 3D orbital, 4D orbital, 5D orbital. So here we can sum up like this: 1s orbital and 2s orbitals having, so that is there, the 4s is the size of the orbital increases when the n is increases, the quantum number is increases. So that is why, so 4s is more than 3s, sorry, 4s is less than 3s, 3s is less than 2s, and 2s is less than 1s. So in 2p orbitals, here there are three orbitals are there that it can be designated as 2pxy, 2pyz, and 2pzx, 2pz. Okay, here the probability density of the energy and size of the various orbitals are becomes 4p is more than less than 3p, and 3p is less than 2p. And finally, the 3d orbitals, d orbitals, say it is d orbital. D orbital we can designate it as 5d orbitals, that is dxy, dyz, dz, dxz or dzx, dx square minus square, and dz square. So here the 3D and 4D, 5D, all the orbitals are similar in shapes, but their size and energy is different. I hope students you understood this topic. Thanks for watching this video.